Lab number 1, motion of object undergoing constant velocity. The purpose of this lab is to extract data from real observations and using it to create a computational model by applying appropriate physics principles in order to gain a better understanding of motion laws involved in common interactions. Furthermore, following through the procedure will help build experience with the tracker software and E Python coding, which will aid in solving future physics problems involving an iterative approach. Thus, this lab seeks to answer the question, to what extent does Newton's first law apply to objects moving at constant velocity? Two fundamental principles are used to derive equations necessary to create our computational model. Newton's first law describes an object's tendency to remain in either motion or rest, leading to the position update equation, which enables us to calculate an object's position based on given velocity and time interval. Newton's second law states, an object's change in momentum is directly proportional to applied force. The derived equation is used in this lab to explain how a zero net force would result in a constant velocity throughout motion. The first step of the lab involves recording a video of an object moving at constant velocity with a consistent center of mass, in this case a basketball rolling across the floor. Using Tracker, extracting the object's position in each video frame creates a plot sorting the change in position according to the change in time. Information required for the computational model can be extracted using data from Tracker. Recall that only the changes alongside the horizontal x-axis are considered, for the object is observed to be moving along a straight line from positive x towards negative x. The computational model should also assume constant velocity throughout. Mass of the object is measured and initial position is set as the position vector recorded when time equals 0. Initial velocity is calculated by measuring the position traveled between time at 0 and position at the immediately following frame divided by the time interval 1 over 30 seconds. The computational model will generate only up to the final time span of the video at 1.2683 seconds. The following data is used to replace code from the given starter code to create a model that best fits the given observation. Note that line 57 and 59 have been modified to suit Newton's second law and position update equation in general form for it to continue updating for repeated calculation between each time interval. A print command is added to the end of the while loop in order to extract numerical data table from the computational model as well. Following is the animation and graph generated when running the final computational model. By observation, the animation is very similar to the observed motion from the video, as seen by the ball moving towards left, as well as the downwards moving graph over time, indicating movement towards the negative x-axis over time. The following graph is produced by plotting both observed and computational model data onto the same coordinate plane, comparing the likeliness of two data sets. Overall, the computational model appears to match the observed data very closely, indicating that Newton's first law significantly holds up during the motion observed. However, a discrepancy is observed beginning some point between time at 0.5 to 0.7 seconds, where the ball appears to travel in increasing position increments until the end of observation. This slight increase in velocity indicates a force applied on the ball, which is assumed to be gravitational attraction caused by the gradient of the ground surface the ball was rolled on. In conclusion, the observation strongly holds up to Newton's first law, but shows a small discrepancy from the expected model due to environmental limitations of creating a completely non-interacting surrounding. In order to overcome these errors, a future experiment could be conducted using smaller time intervals by filming at 60 frames per second to reduce the extent of interactions of surroundings. An alternate rolling surface such as a smoother and flatter ground would also aid to minimize interactions by reducing friction onto the ball. If the position axes were to be flipped, the only change would occur through the opposite signs of the position vectors recorded, but with the same absolute values. The time versus position graph would be demonstrating the same slope and starting point, but only this time pointing upwards instead of downwards. When assuming zero net force applied to the object during motion, it is difficult to state the total number of forces since the net force already summarizes the sum of the forces coming in from all possible directions at undistinguishable magnitudes, which eventually sum up to 0. We could predict air resistance, friction, gravitational attraction to all contribute some force based on observations of the surrounding, but they ultimately cancel out to give zero net force and a constant velocity. And thank you for watching.